So in order to understand the modal pushover analysis, we first have to understand the idea of the effective earthquake forces uh, on which are applied on the multiple degree of freedom system. So this is a prerequisite concept uh, which we have to first discuss, and then we will be able to proceed to the modal pushover analysis. The idea is that we start with the governing equation of motion for multiple degree of freedom system. This is the equation for a multiple degree of freedom subjected to a ground shaking. So we have a structure which have some mass matrix and a K matrix and a C matrix, mass, stiffness and damping matrices. It is subjected to a ground shaking which is represented by UG dot dot function of time. This is ground acceleration. So this equation is the governing equation of motion for this structure subjected to UG dot dot. On the right hand side you have minus mass matrix times one vector. One vector takes care of this fact that some of the degrees of freedom in the structure may not be in the direction of the applied ground shaking. So for example, if this is a structure which has 10 degrees of freedom, your mass matrix will be 10 by 10, your K matrix will be 10 by 10, and your C matrix also will be 10 by 10. In this case, your one vector will be 10 by 1 vector, and it will have only two numbers, ones and zeros. Ones corresponding to those degrees of freedom which are in the direction of UG dot dot. Let's say that the earthquake is applied in the horizontal direction, and first 5 degrees of freedom in this structure are in the horizontal direction, right? And then the next 5 are, let's say, in the vertical direction. So my one vector will be, first 5 degrees of freedom are in the direction of earthquake, so they will be 1 1 1 1 1, and then next 5 degrees of freedom will be not in the direction of earthquake, so they will be 0 0 0 0 and 0. So this will be my 10 by 1 1 vector, right? So it is called influence vector, sometimes represented by 1 or I, influence vector, right? So this m into I is the load pattern which is multiplied with this time function, because this whole thing on the right hand side is the effective earthquake force. So effective earthquake force is minus mass matrix times one vector times UG dot dot. Now UG dot dot is just a function of time, right? And minus m into 1 is representing, actually m into 1 is representing the spatial distribution of these forces, how the forces are distributed along the height of the structure, right? So UG dot dot are telling us the temporal distribution of forces, how the forces are fluctuating in time, and m into 1 is telling us that how the forces are distributed along the height, right? So they are mass proportional. Depending upon the mass matrix, the forces are distributed along the height. So let's represent that m into 1 as S vector, right? So now the concept is called the modal expansion of excitation vector, which have the form P of t equal to some S times P of t. Let's say that we have some forces P of t which are defined by a product of two quantities. One is representing the spatial distribution along the height of the building, and other quantity is telling us that how those forces are varying in time domain. So this is time variation, spatial variation and time variation. These two separate quantities are multiplying to make this P of t. The idea is that we can expand that spatial distribution vector into contributions from different vibration modes. So we can say that this S is the sum of SR vector, where R is 1 to n, where 1 to n are the number of mode shapes. And then we can represent this SR as this gamma R, which is the modal participation factor, times the mass matrix times the mode shape R. So if we expand that term, if we expand that summation, it will spatially look like this, like this. Let me show you here. Yeah, this one. So you have some vector which is representing the spatial distribution of forces, which can be any distribution. It is expanded, it is equal to some regular shape or mode shape distribution, sum of the mode shape distribution. So this is the first mode, then this is the second mode like this, then this is the third mode like this. So if you look at the direction of these forces are corresponding to mode shapes like this. This is the fifth mode and so on. So you can sum these forces to reproduce the same spatial distribution. This is the idea called modal expansion of a particular vector. That you have some vector which has any spatial distribution, let's say it is S. You divide it as a sum of S1, S2, S3, S4 up and so on, and each S1, S2, S3, S4 is representing the shape of one mode, right? So you sum those different modal spatial distributions to reproduce the same S, right? So it is the idea called modal expansion of the effective earthquake forces, which is the basis of modal pushover analysis and the uncoupled modal response history analysis. So I again come back to the same slide, that I have expanded this S as a sum of contributions from different vibration modes are equal to 1 to n. This is the summation. So this equation can be viewed as an expansion of the distribution S of the applied forces in terms of inertia force distributions SR associated with natural modes. So we can pre-multiply this above equation by phi n transpose and use the orthogonality property of mode shapes to come up with this expression. Then we can rearrange it to have this expression, which simply says that the nth mode's spatial distribution will simply require the modal participation factor of that mode multiplied by the mass matrix multiplied by that mode shape. Since these two quantities are constant quantities, mass matrix and modal participation factor for a particular mode, so therefore the Sn will have the same spatial distribution as phi n or the mode shape. So this idea is further applied to the effective earthquake forces. So this idea in the last slide is for any P of T which have this form, that it is a product of two quantities. One is showing the spatial distribution and other is showing the time distribution or time variation. Now apply that idea to the effective earthquake forces. Effective earthquake forces also have the same form, that this product is telling us the spatial distribution and this function is actually the time distribution. So let's represent this m into I as S vector, and let's now expand that S vector as a sum of Sn, where n can be 1 to capital N, total number of modes, and then we can simply say that S can be summation of gamma n m into phi n, where n equal to 1 to n. This factor is called the modal participation factor, and for any nth mode, if the mode shape is available and mass matrix is available, we can calculate that using this expression ln over mn, where ln is phi n transpose into m into I divided by phi n transpose into m into phi n again. So all we need to have is these two quantities to calculate the modal participation factor of that mode. So first we calculate mode shapes, then using mass matrix and that mode shape, we calculate the modal participation factor for each mode, and then using that expression, we can expand our S vector into the contribution of each mode. Now, applying that idea to the effective earthquake forces, our effective earthquake forces also can be decomposed into the contribution of modal effective earthquake forces. So P effective comma N is now the part of effective earthquake force which is contributed by only the nth mode shape, right? So we have expanded the total earthquake force, which is randomly distributed along the height, into contributions of the modal effective earthquake forces. Each modal effective earthquake forces will have the same pattern as that particular mode shape, as shown by that figure which I show next, right? This one. So now the total P effective is the sum of P effective N, where N can be 1 to N is the number of mode shape, and that can be again written as this one, because we have already know that this P effective N can be written as Sn into Ug dot dot, right? So the contribution to the nth mode to total P effective and S are this one, right? And Sn can be calculated using this expression, modal participation factor time mass matrix time phi n. So the idea is that we expanded the effective earthquake forces into modal contributions. So the total earthquake force, which was originally, if this is the structure, if the total earthquake force was a random force like this along the height, we actually divide it into few modal patterns, right? So this is first mode. This is actually the P effective 1, P effective comma 1, plus this is another load pattern, which is the second load pattern like this. Some forces are applying this and the other are in opposite direction. This is P effective 2. Similarly, P effective 3, P effective 4, 5, 6. You sum them and you get the total P effective, right? So the spatial distribution of the effective earthquake forces are decomposed in the form of modal contributions. So now you can apply one separate load pattern. Obviously all of them will be the function of time also, because the P effective is function of time, but the spatial distribution is you can say decomposed into different modal contributions. So the pattern along the height is now decomposed into mode shape patterns. The time variation is still same, Ug dot dot is still same, so it is still being multiplied by each of the P effective n, but Sn is different for each mode now. Sn is actually coming from this equation at the bottom. It depends on that mode shape, right? So P effective comma 1 will be this one, a pattern which is the same shape as the first mode. P effective 2 will be this pattern. Obviously this pattern will still be fluctuating with time, but the pattern will remain same. Pattern will be defined by this S1, S2, S3, right? And the same idea is depicted here in this figure, that you will have some distribution of applied loading, some irregular pattern, and this irregular pattern is approximately equal to the contribution of first few vibration modes. So if you sum all these forces or all these patterns, you will reproduce the same irregular looking pattern. And at each instant this is happening because the actual loading pattern is fluctuating and the mode shapes are also fluctuating with their own frequencies. So therefore at each time instant when you sum them, you can always reproduce the original irregular or random pattern, right? So this concept of modal expansion helps us in decomposing the earthquake force into some simple mode shape patterns or modal inertia patterns defined by this equation at the bottom, which is this one, right? That you can simply multiply that mode shape with mass matrix with the modal participation factor and you get a pattern of that mode shape, right? That pattern can be simply multiplied by the applied earthquake and it can be applied as the effective earthquake force of the nth mode only, right? So you may now with this idea instead of applying the total effective earthquake force to your computer model, you can also apply the nth mode contribution to your computer model, which is only from a particular vibration mode, right? And then you will see that the structural model will only respond in that particular mode when you apply P effective for that mode. So for example, for first mode, if I apply P effective comma 1 of T, Chopra actually showed that in his book, that if you apply the P effective 1 to your structural model, the response will only be primarily in the first mode only, because you apply the first mode's effective earthquake forces. Similarly, if you apply the effective earthquake forces of second mode, the response will primarily be in the second mode of that building. The response from other modes will be very less, almost negligible, right? So using this effective technique, we can decompose our applied loading into the modal contributions. So each mode's loading can be applied separately, and the spatial distribution of each mode's loading is represented by this equation, and it is the same spatial distribution as that particular mode shape. So based on the modal expansion of these effective earthquake forces, Chopra and Goel actually developed two seismic analysis procedures, approximate seismic analysis procedures. One is called the uncoupled modal response history analysis, and second is called the modal pushover analysis. The UMRHA, or uncoupled modal response history analysis, was not originally developed to be a specific or separate seismic analysis procedure. It was developed only to provide a basis or conceptual rationale for the modal pushover analysis procedure. The idea in the UMRHA procedure is that the response history of the building to the nth mode's effective earthquake force is determined by the nonlinear time history analysis of an inelastic single degree of freedom system, which is representing that particular mode of the building. And you do that for enough number of modes and then superimpose the responses of those modal single degree of freedom systems to get the total response. So you develop a nonlinear single degree of freedom system for each mode separately, apply the earthquake to that mode separately, and then combine the time history responses to get the total time history response of the multiple degree of freedom system. So in this case, the UMRHA procedure is an approximate dynamic analysis procedure, but it is highly approximate and it has few assumptions. The modal pushover analysis, on the other hand, is a nonlinear static procedure. It is a pushover analysis procedure, and the idea is that we apply the peak response, we directly get the peak response of the nth mode's effective earthquake forces by just pushing that building in that particular mode shape using the modal inertial load pattern of that mode only. We push that building and get the seismic response of that mode only, and we do it for enough number of modes, and separately we do that and then combine the peak responses obtained from the pushover analysis. All of those pushover analysis procedures, we combine the peak responses by any modal combination rule, just like the response spectrum analysis, SRSS, right? So in the modal pushover analysis procedure, we actually perform more than one pushover analysis, one for each mode separately, and then combine the peak response using the statistical combination rule like square root of the sum of squares or CQC method. So both of these procedures are based on the idea that the effective earthquake forces can be decomposed into the sum of P effective N, which is the nth mode's contribution. So effective earthquake force P effective total is actually it is actually decomposed or expanded as a sum of P effective N. Each will be the function of time, obviously, and n can be from 1 to capital N, the total number of modes, for example. So, and the spatial distribution of P effective n is actually represented by Sn, and the time variation is represented by the actual earthquake time history UG dot dot. Sn can be determined using modal participation factor, mode shape vector, and mass matrix, right? So this is the overview of the concept of modal expansion of effective earthquake force. So next we will apply this concept to understand the uncoupled modal response history analysis and then the modal pushover analysis procedure, right?